Okay, so the last section we are going to look at this week is 4.2. As I said, we're going to split that up into 2 days. So we're going to look at part 1 today and part 2 tomorrow. 4.2 is all about graphing. Okay, so there'll be very little like solving rational equations in this section. It's more graphing functions. 4.3 is all about solving rational equations. So we'll get to that next academic week. All right. Does anybody remember if I graph something like this, x minus 3 divided by x plus 5, what value would make the denominator 0? -5. And at -5, we would have a what? Does anybody remember what it's called? Yeah? No, not a hole in this one. We would have a vertical asymptote. And the reason we would have a vertical asymptote is because there are no common factors. Now, if I did something like this, how many values would make the denominator 0 in this one? 2. What are the 2 values? 2 and -3. What would happen at 2 on your graph? That would have a hole in it. Yep, because there's a common factor. What would happen at -3 on your graph? You would have a vertical asymptote. Yep. So once you know that a value makes the denominator 0, then you can ask an additional question. Does it cause a hole in the graph, or does it cause an asymptote in the graph? Both of them are undefined, but they look very different. So if the numerator and the denominator have a common factor, then you can get a discontinuity that you can't see, or usually you can't see with the calculator. I know yesterday we graphed one and we were able to see it. Again, I've never seen the calculator do that before. It just must have been the right window and the problem I used. It just happened to work. But generally you can't see it. Right? Let's try graphing the one on the right and see what it looks like. So it's x minus 2 over x minus 2, x minus 3. All right, so we've got x minus 2 divided by x minus 2, x minus 3. Okay, and I typed it in with double parentheses around the denominator, so it does the whole denominator first, and then I put the parentheses around the x minus 2, x minus 3 to let it know it was distributive. So that's why I typed it the way I did. Let's check 2 and -3. Error. And, oh, I must have typed something in wrong. Yeah, it's x plus 3, not x minus 3. Okay, so now positive 2 and -3 both give us an error. But at 2, we said there's a hole. At -3, there's an asymptote. Let's see what that looks like. There's the asymptote at -3. Okay, I think it's pretty clear to see it. I'll make it a little bigger. So there's your asymptote at -3. And now look at what happens at 2. Does it look like anything happened at all on the graph? Right there. No. Just looked like it went right through it. And that's what it usually does on the calculator. So when you have a hole in the graph, you generally can't see it. I'm not going to do this one because it's pretty similar. But if I graph f of x equals x minus 1 over x minus 1, what would cause the denominator to be 0? 1. Now, would it be a hole at 1 or a vertical asymptote? That would be a hole because there's a common factor. Okay. How about here? Still 1 would make the denominator 0. Hole or common factor? I'm sorry, Whole or asymptote?
That'd be whole. Because there's still a top factor.
Right, it's still x minus 1 squared just means you have the same factor twice. But it's still a common factor between the top and the bottom. Yep. So it would again be a whole. So we've been calling it a hole in the graph. The real name for it, it's called a removable. Or you can kind of think of the word removable as meaning hidden. Right? So a removable discontinuity is called a hidden discontinuity because you generally can't see it on a graphing calculator. So if you see directions that say find all hidden discontinuities, that's the same thing as saying find if there are any holes in the graph. And in our particular problem that we just did, the hole in the graph was at 1. What if I changed this top number to a 4? Where would the bottom be undefined now? Still 1. I didn't change that. The bottom would still be undefined at 1, but what would happen at 1 now? It would be a vertical asymptote. Yep. And it would be very obvious on the graph. So, any question on what it means? Or any question on that other term for a hole, removable discontinuity?
Can you really explain the definition of this?
A removable discontinuity, it's just a hole in the graph.
Okay.
Yeah.
What would that look like?
When you sketch it. So if you have to sketch, like let's say you had a line and it had a hole in it, that's how you sketch it.
So it would show up like that on the graph?
When you draw it by hand, it should, yes.
Oh, okay.
The calculator won't do that though. The calculator will probably just show it like it did here. It'll just draw straight through it. You won't even know there's a hole looking at the graph.
Okay.
All right. So what we're going to look at is problems like this now. Okay. What I wrote on the left, that just represents a generic polynomial. So you know what? Let's yeah, that's fine. I'll leave it like that. What exactly is in the top and the bottom? Well, I don't know. That would depend on the problem. You either could have something like this or something like in the bottom. The important thing here is as you look at the polynomial, the exponent goes down each time till finally you end with a constant, like a +1 or a -1, but you finally end with a term that doesn't have a variable. This is called the leading term. It's the term, in that case it's in the top, that has the highest exponent. That is the leading term that's in the bottom. It's the term in the bottom with the highest exponent. The only thing that's going to matter for what I'm going to show you next is the term with the highest exponent. Nothing that comes after it makes a difference. Okay. Not the term with a lower exponent or the constant or anything else. Just the term with the highest exponent. All right. So if I had something like this. In chapter 3, we talked about what was called an EBM. That was the end behavior model. Does anybody remember, for that polynomial, what term basically predicts what that would look like? Yeah?
4x cubed?
4x cubed. So what that means is if I graph the original problem, 4x cubed minus 8x plus 2, and then I graph 4x cubed, if I zoom out enough, those two graphs should basically look the same. Okay. So let's try zoom 6 and let's just see how they look. 1. And the bottom one is 4x cubed. Okay, so in that view, I wouldn't say they look exactly the same. But that's because I'm not zoomed out. Okay, let's set our y min to negative 200, and let's set our y max to 200. So now we're going to look at the big picture. Okay, there's the top one, and now here's the EBM. How close do they look now? Pretty close, right? Not exact. The EBM will never be exact, but it should be really close, right? So this is a simplified version of what that looks like. It takes out some of the details, but it gives you a simpler overall picture. We want to learn how to do the same thing with something like this. There's a lot of details here because of all these extra terms. What we want is a simpler version of that formula. So what I circled in red, that's the EBM of the top. What I circled in black, that's the EBM for the bottom. If I want to find the EBM for the entire thing, what do you think I would do with the EBM for the top and the EBM for the bottom? I would divide them, exactly. So to find the EBM for a rational function, you find two EBMs, the one in the top, the one in the bottom, and then you divide them. So let's say, EBM for the entire thing, not just the top, not just the bottom, the whole thing. The entire rational function is the EBM of the top divided by the EBM of the bottom. And the whole goal of the EBM is to give us a simpler formula to work with that would basically look the same if we zoomed out enough. That's the point. Okay, so the EBM for the entire function is the EBM of the top divided by the EBM of the bottom. So now, let's try that here. So it says find the EBM, and then I'll show you how you get the horizontal asymptote. The horizontal asymptote is going to be a lot easier to do now than we did yesterday. You're not going to have to do any kind of long division here. We're going to be able to use the EBM to find it faster. All right. So let's start with example A. What's the highest degree term that's in the top?
2x squared.
Yep, it's 2x squared. And if it helps, you could think of it like this. Might help when you cancel things out. So it's 2x squared. What's the highest degree term in the bottom?
3x cubed.
3x cubed. And what can you cancel from the top and the bottom? 2 x's. 2 x's from the top, 2 x's from the bottom. And what does that leave me with? 2 over 3x. That is the EBM. Now, how do you use that to find the horizontal asymptote? So to find the horizontal asymptote, let x approach infinity or negative infinity in the EBM. So in other words, let the x become a really, really big number that's positive, or a really big negative number, and tell me what would happen to what's in the box. So this is kind of like what we did yesterday a little bit. The nice part now is I don't have a really complicated formula to look at. I have a much simpler version, and it's going to give me the same answer as looking at the more complicated version. Okay. Would it give you the same answer for all kinds of little details? No. Would it give you the same answer for the horizontal asymptote? Yes. That's why we do it. Okay. So first of all, horizontal asymptote is always what letter by itself on the left? Y equals. And now let's look at our EBM. As the x gets bigger and bigger and bigger, what's going to happen to the bottom of this fraction?
It's bigger.
The bottom of the fraction is going to continue to get bigger. What's going to happen to the entire fraction? It's going to get smaller, and it's going to get so small that it's going to approach what number? It's going to approach but never reach 0. That's how you find your horizontal asymptote. So you use the EBM to get a simpler version of your formula, and then you use that to find the horizontal asymptote. Okay, just to be clear, you cannot use the EBM to do everything. It's a simpler version, but you do lose some things by making it simpler. You lose a lot of detail. But when you're looking at an asymptote, asymptotes aren't about detail. They're about big picture. And an EBM is perfect for the big picture. Yes?
If you plugged in the EBM, would you get the graph too?
You would get a graph that looks similar if you zoom out enough. Kind of like, it would look kind of like this one. It would be close, but it wouldn't be exact. But it's the big picture.
Could you get the horizontal asymptote from just looking at the graph?
The original one?
Yeah.
Yes, you could also graph the original problem and look at a graph, and you would get the horizontal asymptote.
But you can do that with the EBM. It would be a different graph.
No, if you graph these two, they would look very similar. Yeah, they would look like if I type them in, if you type in 2x squared plus minus 1, and then you divide by 3x cubed plus 2x plus 1. Okay, make sure I put all that in, right? And now you put in 2 divided by 3x. Where these graphs are not going to look the same is in this area, near the origin. They're going to look very different. Where they are going to look the same is way out here and way out here, way out on the left and the right edges. That's where they're going to look the same. Okay. So let's do zoom 6. Okay, so kind of weird stuff can happen in the middle, but what I want you to do is look at the left and the right edges and look at the graph. If you look at the left and the right edges there, does it look like, it's kind of hard to see. Does it look like the red and the blue graph trace over each other on the far edges? Yes. So the far edges are the horizontal asymptotes, and the blue and the red graph have exactly the same horizontal asymptote. Where I told you they would look different is here, towards the origin. And they do. They don't look the same there. But that's not what an EBM does. The EBM should look the same out here and out here. Okay? So the EBM in that case is y equals 0. All right, let's look at this one. Just move that down a little bit. Or flip it over. Okay, so we got our next problem. What's the highest degree term that's in the top? 2x to the fourth. What's the highest degree term in the bottom?
3x to the fourth.
3x to the fourth. And same thing we did before. We're going to cancel out anything we can. What can we cancel out from the top and the bottom?
All of the x's.
All of the x's. You have 4 x's in the top, 4 x's in the bottom. And what does that leave me with?
2/3.
Leaves me with 2/3. That is your EBM. Okay, now the horizontal asymptote. We do the same thing we did up here. To find the horizontal asymptote, let the x that's in this box get bigger and bigger and tell me what's going to happen in that box. So when we did that before, it made the box 0. What's going to happen this time as you let the x get bigger and bigger?
There is no X.
There is no x. So what happens as x gets bigger and bigger to the number in the box?
It's gonna stay the same.
It's going to stay the same. Nothing happens to it. So in this case, your horizontal asymptote is y equals 2/3. One of two things is always going to happen with the EBM today. Either you're going to be left with more x's in the bottom, you'll be left with an x in the bottom, and your asymptote is going to be at 0. Or you're going to have the same amount of x's in the top and the bottom, and they're all going to disappear. And then horizontal asymptote is going to end up being whatever two numbers were in front of the x's. But that's the only thing we're going to look at today. Either you're going to have more x's in the bottom, or you're going to have the same number of x's in the top and the bottom. We won't be looking at more x's in the top today. All right. So any question on how we found the EBM or the horizontal asymptote for this one? Or for that one? Okay. All right, so last thing we're going to look at is doing some sketching. And the type of sketching we're going to do is exactly what I just explained. The exponent in the top will always be smaller than the bottom or equal to the bottom. So here's one we're going to do where the exponent in the top is equal to the bottom. Here's one we're going to do where the exponent in the top is smaller than the bottom. But those are the two types. Okay, so rational functions are complex. Okay, there's a lot of different things going on in the graph. That means when we sketch them, there's a few steps we have to follow. Okay. One thing that is helpful to find when you're sketching them is where they cross the axes. The x-axis and the y-axis. If they cross the axes, it is possible you could have a graph like this. I think we looked at one like this yesterday. That's a graph where both the x and the y-axis are asymptotes. So step 1 would not apply to this problem, because the red graph never crosses the axes. So there are no intercepts. But if they do cross the axis, those are helpful points to find. Okay. Once you figure out where your graph crosses the axis, if it does, the next thing you want to find are the vertical asymptotes. Yes? Yeah. Okay. The vertical asymptotes are where the denominator is equal to 0. Hopefully, if you get a nice problem, the denominator will factor and you get nice answers. If the denominator doesn't factor, well, then we're going to have to use quadratic formula and we're going to have very not nice answers. Okay? But a lot of them will factor. Once you find your vertical asymptote, the next thing you want to do is get your horizontal asymptote. The easiest way to get the horizontal asymptote is to take your formula and simplify it and work with the simpler version. That simpler version is called the EBM. All right, so we're going to get the EBM and use that to get the asymptote. At this point, now we're going to start using the calculator. We're going to use the table because what we need now is we need some more points. Okay, we're going to have some asymptotes, and you might have the y-intercept and the x-intercept, but you need more points. What you need is a couple points near each asymptote. You can't find a point on the asymptote. That's an error. But you can find a point near the asymptote. And when I say near, I mean on each side. So if you had an asymptote of 2, I would look at what happens at like 1.99. That's the left side. And I would look at what happens at 2.001. That's the right side. So you're going to evaluate your function near each asymptote. And if you want, at this point, you can use additional points if you feel it's necessary. You might feel like you have enough information at that point to do it, or you might say, you know what, I still don't know what this graph looks like. I'm going to plug in a few more points so I have more detail when I draw my line, in this case, curve. And we can always double check the answer on the calculator. All right, so there's a lot of different steps, but the nice thing is a lot of these graphs look the same. So once you have an idea of what a certain type looks like, then you kind of know what you're looking for every time. So for example, there's one type that kind of looks like this. Kind of has like a curve in the upper left, another curve in the lower right, and then kind of like an S in the middle. Okay, that's a pretty common shape that we get when there are 2 vertical asymptotes. And I think the first one we do is going to look something like that. Okay, so let's try that. So we are going to sketch x minus 1 over x squared minus x minus 6. Okay, first let's make sure this fits the kind of problem I said we were going to do today. What's the degree in the top? 1. Degree in the bottom? 2. Today we are sketching problems where the degree of the top is less than or equal to the bottom. The degree in the top is a 1. The degree in the bottom is a 2. Yes, 1 is less than or equal to 2. Yep. Okay. So it does fit the kind of problem we're going to do today. Let's start with our intercepts. Let's do the x-intercept. The x-intercept is when you plug in what number for what letter?
0, x, or no, wait.
When you plug in 0 for y. Well, I don't see a y anywhere in that equation. So, well, where's my y then? It's the f of x. That is my y. So plug in 0 for that. And now we're going to solve it. Now, we can simplify this because the only way that you can have a fraction equal 0 is if what happens? How does a fraction ever come out to 0? Yep.
If the top equals 0.
If the top equals 0, who cares about the bottom? We care about the bottom for other things, not for the x-intercept. So just figure out what would make the top 0. In this case, what would make the top 0?
1.
1. That is your x-intercept. X equals 1. Okay, let's do the y-intercept. The y-intercept is when you plug in what for what letter?
0 for x.
0 for x. So let's plug in 0 for x. What do you get in the top if you plug in 0?
Negative 1.
-1. What do you get in the bottom if you plug in 0 for x? -6. Your y-intercept is 1/6. So just a little bit above the origin. Not a heck of a lot of help, but we've got those 2 points. Okay. The next thing, find the vertical asymptotes. That's the zeros of the denominator. So here's our denominator, x squared minus x minus 6. What could I try to do to find the zeros of my denominator so I'm not looking at a quadratic anymore? Yeah? Factor it. Yep. So it would have to be an x and an x. What about my signs in the parentheses? You have to have a plus and a minus. And 2 numbers that multiply to give me 6 and subtract to give me 1. 2 and 3. So we just have to make sure we put them in the right spot. Yep. That's minus 3x plus 2x is minus x. So that's perfect. So it factored nicely. Are there any common factors there? I should ask that first. No. Since there's no common factors, that means this graph doesn't have any holes. No holes, all asymptotes. What would you plug in for x to make the first factor 0? -2. And what would you plug in to make the second factor 0? 3. Okay, let's graph those asymptotes. Let's do -2. And +3. Every time you draw a vertical asymptote, that breaks your graph into a new piece. So this graph is going to be in 3 sections: a left, a middle, and a right. Okay, so we got the intercepts, we got the vertical asymptote. Next thing is the EBM to get the horizontal. Okay, let's do our EBM. What's the highest degree term in the top? That's the degree of the highest term. What is the term itself?
X.
X. And what is the highest degree term in the bottom? X squared. And what does that give me for an EBM? 1 over x. And now that allows me to get my horizontal asymptote. Let x get bigger and bigger and tell me what happens to the EBM. What number will 1 over x approach as x gets really big? 0. Okay. That's your horizontal asymptote. All right. So we've got all our asymptotes. That gives us some kind of boundaries when we're sketching. We've got a couple points, but we need some more points. Now, to get more points, I could plug them in by hand. Right? Just change all the x's to whatever number you want to use. But I could make a mistake, and it's going to take a while. So I want to use the table just to plot points faster. Okay, so So let's do x minus 1 and divide by x squared minus x minus 6. Second table. Now, don't plug in the asymptotes, because if you do, you're just going to get an error. That does nothing. That doesn't help me. But I want to plug in numbers near the asymptotes. Let's start with this left asymptote. It was at -2. What is a number just to the left of -2 by extremely close to it? When I say close, I mean within like 100th or 1,000th of it.
-2.0001.
Yeah. So just to the left of 2, I am way down at -600. That means my graph is heading towards what? It's heading towards -infinity. So all we're going to do is put a dot as far down as you can. And your graph is going way down there. Now I want to check just to the right of -2. What's a value that's to the right of -2, but really close? Yep.
1.99. Or -1.99.
-1.99. Okay. And we are up at 600. So just to the right of that dotted line, we're heading towards what?
Infinity.
Infinity. So just put a dot up as high as you can. All right. Now let's check the other asymptote. We're at 3. What's a value that's just before the number 3? 2.999. We're at -400. So just before the number 3, our graph is going way down. And what do you think is happening just after the number 3?
It's going way
It's
up.
going to be going up. Yeah, it's always opposite, but you can check. We're up at 4,000, so it's going up very high. Okay, so in the middle, I think I have enough points. I have 4 points in the middle section. Okay, you have to stay very close to the vertical asymptotes as long as you can, but you also have to go through those 2 red dots in the middle. So basically it has to stay as close as it can, but eventually it has to start to curve away from it, go through those dots, but it can't keep going to the right because it hits another asymptote, and that's what the middle section looks like. It's kind of like an S shape. Now let's check the right section. We only have 1 point in the right section. What would be another x value that would be in this right section? Yep, we could do 5, we could do 6. At 5, they're pretty close. At 5, we're at about 0.3. So 1, 2, 3, 4, 5, right about 0.3. At 6, basically the same, just a tad lower, 0.21. So what's going to happen in this section? It's going to stay very close to that asymptote, but eventually it has to curve. You can go through those dots and then get closer and closer to the horizontal. So it's perfectly fine to cross the horizontal asymptote in the middle, but you don't want to cross it as you keep going to infinity. Okay, now in the left section, we've got that 1 point. What's another x value that's in the left section?
-4.
Sure, we could do -4, and we get about -1/3, roughly. 1, 2, 3, 4. -1/3. And that's enough information, I think, to see what's going on. We have to stay very close to that asymptote, but it has to start to curve. And that other asymptote, it's like a wall that it can't go past. And that's pretty close to what our graph is going to look like. I think this middle might be a little flatter than I drew it. But I think we've got a really good sketch. So that's what that one looks like. All right, any questions on that? All right, we'll try one more of them, but it's really going to be the same steps again. Okay. So is there any part of the information that we found as we were going through it that you're unsure how we did it? Okay, so that's how I do it. I put all the information kind of off to the side, and then next to it I put my sketch using it. All right, let's try this one. What's the difference between, I'll put them both up at the same time, the problem that we did before and the one we're going to do now? Yeah?
They have the same, they both have two, like an x squared, squared.
Yep, and what do we call that? Yep.
The EBMs are to the same degree.
Yeah, the EBM of the top and the EBM of the bottom are the same degree. Yep. All that that's going to do is cause the horizontal asymptote to move up or down. It's not going to be at 0. Everything else about that graph is going to look pretty much the same. All right, let's, it doesn't matter what we start with, but I just put vertical asymptote first. Okay. The bottom only has 2 terms, so all you can do is factor out the GCF. What's the GCF between the 2 terms in the bottom?
X.
X. And what does that leave you with in parentheses if you factor it out?
2x minus
2x minus 5. Perfect. Okay, so that's going to make the vertical asymptotes a little easier to figure out. We can try to factor the top, just to make sure there's no common factors. 3x and x. What kind of signs would we need?
A plus and a minus.
We would need a plus and a minus. Let's switch them. Try it that way. Plus and minus. I don't know, I might have had it right the first time. And 2 numbers that multiply to give me 4.
2 and 2.
We could try 2 and 2, or we could try,
1 and 4.
I would try 1 and 4. Let's see if that works. That gives me 3x squared. What's negative 3x plus 4x? X. It's perfect. So that's how the top factors. Okay, so first, any common factors between the top and the bottom? No. No common factors means that there are no
Holes.
holes. No holes in this graph. Okay. How many different numbers would make the bottom 0? Two. Yep. What could you plug into your first factor to make that 0? 0 itself. And what could you plug into your second factor? 2.5. Yep. Okay, I'm going to sketch those as I go. So those are my vertical asymptotes, 0 and 2.5. Okay, so I've got 0 and 2.5. All right, so that's my vertical asymptote. What do we usually find that helps us get a simpler version for the horizontal asymptote? We
EBM.
need the EBM. Yep. So I'm going to put that under here. Okay. What's the highest degree term in the top?
3x squared.
Highest degree term in the bottom? 2x squared. X squareds are going to cancel. And what am I left with for an EDM?
3 over 2.
3 halves, 3 over 2. Now, I can do my horizontal asymptote. As x gets bigger and bigger, what's going to happen to the number in this box?
It's gonna stay the same.
Nothing. It's going to stay exactly the same because there is no x. So that is your horizontal asymptote. 3 halves, or as a decimal, 3 divided by 2 is 1.5. Yep. So you can already see the same basic grid as the last problem. 2 verticals and a horizontal. It's actually easier when you only have 1 vertical and a horizontal, because then you usually get a graph that looks like that and that. It's a little simpler. There's no middle piece. With us, we get those 2 pieces plus kind of an S shape in the middle. Okay, so we got that vertical, we got horizontal. Let's just try the y-intercept. I'm not going to worry about the x-intercept right now, because I could get that on the calculator if I really want it, by calculating the 0. But anyway, let's just do the y-intercept. How do you find the y-intercept?
X equals 0.
Plug in 0 for x. If you plug in 0 in the top, what do you get when you simplify that? You get -4. And if you plug in 0 in the bottom, what do you get?
0.
So what does that mean?
But it can't be 0.
But it can't.
Right. So since we got 0 in the bottom, what is -4 divided by 0? No.
-4.
No.
Undefined.
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 There is no y-intercept. This graph will never cross the y-axis. And it should make sense that it can't cross it, because look at your asymptote. It's right on the y-axis. You can never cross a vertical dotted line. So you will never cross the y-axis. Okay, so we got the vertical, the horizontal. There was no y-intercept. Let's use the calculator. So now we need to check out some points that are close to our asymptotes. So 3x squared plus x minus 4 divided by 2x squared minus 5x. If you want to check that your 2 vertical asymptotes are right, you can. So we had one at 0, and we had one at 2.5. Well, 0 gives us an error, and so does 2.5. So we confirmed what we already knew. Now let's check what happens close to those asymptotes. You're either going to go up to infinity or down to -infinity. What's a number that's just a little bit smaller than 0, but very close to it? -0.0001. We are at -800. So just before 0, we're heading down to -infinity. So just put a dot as low as you can. Just after 0, we're heading up to positive infinity. Okay, our other asymptote is at 2.5. What is a value just before 2.5? 2 point what?
2.49.
Yeah, I'm going to go even closer. 2.499. We're at negative almost 3,500. So that is heading down. So way down here. What's a value that is just after 2.5?
2.5.
So what we're doing is, this is called evaluating the behavior near the asymptote. We are checking what happens as you get close to it, very close to it. And in that case, we're up at over 34,000. So we're up, heading towards what?
Infinity.
Just after 2.5, we are way up at infinity. Okay. Now, this time, how many points do I have in the middle right now?
2.
It's not enough. So what's another x value in the middle?
1.
1. Okay, 1, 0. There we go. We found the. We just found the x-intercept. What's one more x value?
1.5.
We could do 1.5, and we're at negative 1.5. So 1.5, negative 1.5. So 1.5, negative 1.5, roughly. Okay, so this is a curve. I can see it now, but it's very steep. It doesn't have as much of a flat part in the middle. So it comes down. It's going to kind of curve. And it's going to go like that. What would be another x value past 2.5 that I could check? 5. 5, 3. Close enough. 1, 2, 3, 4, 5. 1, 2, 3. Okay. So that means in this section, it's going to kind of come down, curve, and get closer and closer. And what would be another x value less than 0? Negative 3, we're at 0.6. 1, 2, 3, we're up a little more than a half. So what's going to happen here? It's going to come up, it's going to curve, and it's going to look something like that. Now this time the calculator is not going to do a good job sketching it because it's too steep in the middle. So the calculator is just going to probably give up on it. Let me show you what the calculator does. It's also kind of steep on the left side. Yeah. So look at what the calculator did. It almost looks like it just starts and it doesn't keep going up. But that's not right. This piece should keep going up, and that piece should keep going down. Okay, and everything else there, I think it looks pretty good. Okay. Any questions on that? So similar, pretty similar to the last one. You get the 3 pieces, the 2 curved pieces, and then the S shape in the middle. Not every graph is like that. So we'll look at some other ones tomorrow that are a little different. Okay, so that's homework for tonight. Yeah, on page 234. So that's the first part of 4.2. Tomorrow we'll do the second part. And then Thursday, right now we're on track to have a review day on Thursday. So we have half a section left for the rest of the week. Reminder too, I plan on being after school on Thursday if anybody needs to come by for extra help.